Hey everyone, let's dive right into this explainer and solve the mystery behind Git's most confusing error messages. We're going to do this by looking right under the hood of the version control system we all use every single day. If you've ever felt completely lost trying to fix a broken repository, you are absolutely in the right place.
So let's just start by acknowledging the universal panic we've all felt. You know the feeling? You're right in the middle of a complex rebase or merge, and Git suddenly just halts. It throws this massive block of incomprehensible text at you, completely stopping your momentum. Why do Git errors so often look like a totally foreign language, just filled with strange jargon about heads, refs, and hashes?
Take a look at this. This is our crime scene, an actual terrifying error output from a failed rebase. Error, could not apply F3A9C12. It's intimidating, right? It's incredibly frustrating, it's confusing, and honestly, it usually leads to frantic copying and pasting into search engines, just hoping someone else out there has the magic command to fix it. But today, we're going to validate that frustration by decoding exactly what this actually means. Here's the roadmap for our investigation today. First, the crime scene. Then, the blueprint, the magnifying glass, following the clues, and finally, solving the case. Delving into these internal mechanics is going to help you debug errors with total confidence moving forward.
All right, let's get into it. Section 1, the crime scene.
What's really interesting here is that we first need to shatter the absolute biggest Git misconception out there. The myth is that Git stores diffs, meaning it just stores the line-by-line changes made to files over time. But the fact is, Git actually stores complete snapshots of your project. Every single commit is a full, complete picture of your working directory at that exact moment. Git just computes the diffs on the fly when you ask for them. And because it automatically deduplicates files, an unchanged file costs absolutely no extra storage space.
Moving right along to Section 2, the blueprint.
Now, content addressable storage sounds like really heavy engineering jargon, but it simply means Git is a key value store. The key is a 160-bit SHA-1 hash of your file's content, and the value is the immutable content itself. If you change even a single byte of a file, its SHA-1 hash changes completely. This guarantees absolute data integrity. In Git, you can never actually change an object once it's written. You can only create new ones.
And Git uses exactly 4 object types to build your entire project history. First, we have the blob, which holds pure raw file content without even a file name. Then there's the tree, which acts as a directory listing that maps your file names to those blobs. Next is the commit, which is a snapshot pointing to a tree hash, a parent commit hash, and your metadata. And finally, the tag, which is just a named pointer to a specific commit. Every single piece of your repository is built from combinations of just these 4 components. It's kind of amazing when you think about it. Let's jump to Section 3, the magnifying glass.
By turning this abstract theory into an actionable debugging routine, you can inspect exactly what Git sees right after a failed merge. Step 1. You get the commit hash using git log. Step 2. You read the object type using Git's plumbing command git cat-file t, followed by your hash. And Step 3. Print the raw content using git cat-file p. Doing this completely removes the magic and reveals the raw data that is actually driving your project.
Notice how these objects connect step by step. A commit hash points directly to a tree hash, that tree hash points to blob hashes or subtrees, and the blob hash actually contains your raw file bytes. Tracing this physical path isn't just theory. This visual map is exactly what you use to trace object paths and verify your content for every single fix. This is literally what Git traverses during operations like branch checkouts.
All right, Section 4, following the clues.
Because we humans are terrible at memorizing 40-character hexadecimal strings, Git doesn't make us do it. Branches and the head pointer are simply tiny 41-byte human-readable text files that just contain a commit hash. Creating a branch doesn't duplicate your code, it simply creates a new text file acting as a named reference, pointing right into that immutable object graph we just mapped out.
And that brings us to redefining a notoriously terrifying warning. A detached head is not an error at all. It's really just a literal description of a dangling pointer movement. It simply means your head text file currently contains a raw commit hash instead of a branch name. You can safely look around, run tests, and inspect code. It's a temporary state of observation, not a failure of your repository.
Finally, Section 5, solving the case.
So let's use this translation matrix to decode the Git jargon into plain mechanics. When the error says could not apply hash, it just means your rebase is trying to replay a specific commit object onto a new parent, but the tree objects have incompatible blobs at the same path. Resolving that merge conflict just means helping Git figure out the right blob content by inspecting the hashes so it can generate a brand new commit object. And when you see rig_head in the terminal, it's just the text file holding the commit hash of exactly where your head was before the operation even began.
Understanding this makes recovery so simple. If you want to abort a messy rebase, running git rebase-abort simply restores your head reference to that saved pre-operation commit hash stored right there in .get/org_head. Knowing that absolutely no objects were destroyed during your conflict, and that Git is literally just rewriting a tiny text pointer to abort the process, well, it completely removes the fear of data loss. Your history is immutable and safe.
Understanding these fundamental internals absolutely transforms Git from a black box of anxiety into a logical, highly predictable system. You now have the power to look past the intimidating jargon and see the simple mechanics at work. So, the next time Git throws an error, will you blindly copy-paste commands from a forum? Or will you read the matrix, trace the objects, and fix the underlying graph? The clues are always there. Keep exploring, and thanks for joining me on this explainer.